The Andromeda galaxy played a crucial role in reshaping our understanding of the universe, challenging the notion that Earth occupied a central position in cosmic affairs. It was a watershed moment highlighting that the Milky Way, our home galaxy, was just one of countless others strewn across the vast expanse of space. Advancements in observational technology, particularly the deployment of instruments like the James Webb Space Telescope, have allowed us to peer deeper into the cosmos, unraveling the mysteries of Andromeda. However, recent revelations stemming from data captured by the James Webb Telescope have upended many long-held beliefs about this neighboring galaxy. Over a century ago, the prevailing view of the Milky Way was that of a faint, diffused band of light stretching across the night sky. This perception, influenced by the limited technological capabilities of the time, hindered astronomers' ability to discern individual stars within our galaxy. Instead, various beliefs persisted, often associating the Milky Way with the epicenter of creation, where the celestial and terrestrial realms converged. It wasn't until the 17th century that our perception of the Milky Way underwent a revolutionary transformation, courtesy of Galileo Galilei and his pioneering work with a telescope. Galileo's observations revealed the Milky Way not as a mere band of light, but as an expansive collection of stars, planets, and celestial bodies dispersed throughout space. Building upon Galileo's insights, Thomas Wright proposed a groundbreaking hypothesis in the 18th century, suggesting that the Milky Way was not a random scattering of stars, but rather a flattened disk with our solar system nestled within its confines. However, it was the observations of Edwin Hubble in the early 20th century that truly reshaped our cosmic perspective. Using the 100-inch Hooker telescope at the Mount Wilson Observatory, Hubble identified distant nebulae beyond the Milky Way, demonstrating that there were distinct galaxies in their own right, each containing billions of stars. Among these galaxies was the Andromeda Galaxy, or M31, one of the closest to our own. Andromeda's history of observation dates back centuries, with records of its existence found as far back as the 10th century, when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud. Despite the lack of telescopic instruments, al-Sufi's keen observational skills allowed him to identify Andromeda as a celestial entity separate from the familiar stars dotting the night sky. Detailed observations of Andromeda began in earnest in 1612 when Simon Marius provided a more comprehensive description based on telescopic observations. Later, in 1764, Charles Messier catalogued Andromeda as M31, unwittingly attributing its discovery solely to Marius and overlooking al-Sufi's earlier identification. Significant strides in understanding Andromeda were made in 1864, when English astronomer William Huggins made groundbreaking observations further elucidating the nature of this enigmatic galaxy. Each successive astronomer contributed to the growing body of knowledge surrounding Andromeda, leading to a more nuanced understanding of its structure, composition, and place within the cosmos. Huggins' groundbreaking observations of Andromeda's spectrum marked a pivotal moment in our understanding of this galaxy by discerning that its spectral signature differed from that of a typical gaseous nebula. Huggins paved the way for a deeper exploration of Andromeda's true nature. Andromeda, despite its immense size, is estimated to have a mass between 1 and 2 trillion times that of our Sun. This colossal cosmic structure, residing relatively close to us in the expanse of space, has intrigued scientists for centuries. With an estimated age of around 10 billion years, Andromeda is considered ancient in cosmic terms, hinting at a rich history of formation and evolution. One intriguing aspect of Andromeda's origin is the hypothesis that it formed through the merger of several smaller protogalaxies over billions of years. This process, driven by the force of gravity, gradually led to the formation of the majestic Andromeda galaxy we observe today. Galactic mergers are common occurrences in the cosmos, playing a significant role in shaping the growth and structure of galaxies over cosmic timescales. For a long time, astronomers believed Andromeda to be significantly more massive than our own Milky Way galaxy. This misconception stemmed partly from the perspective of viewing Andromeda from Earth, where its size appears immense. However, recent research has led to a reevaluation of these beliefs, with scientists revising their estimates of Andromeda's mass. Current understanding suggests that the masses of Andromeda and the Milky Way are much closer than previously thought, highlighting the complexities of accurately measuring the mass of galaxies. Andromeda's physical dimensions, however, remain a point of agreement among astronomers, with a diameter of approximately 220,000 light-years. Andromeda surpasses the Milky Way in size, occupying a large region of space. The complexities involved in accurately measuring the mass of galaxies underscore the challenges of studying these immense cosmic structures. Galaxies are intricate systems, and their mass is intricately linked to the distribution and movements of stars, gas, dust, and dark matter within them. This necessitates sophisticated observational techniques and meticulous analysis, which were not available until modern times. One of the most fascinating features of Andromeda is its active galactic nucleus, a highly energetic region at the galaxy's center powered by a supermassive black hole. Observations with advanced telescopes like the Hubble Space Telescope have revealed intriguing phenomena within Andromeda, including 2 points of concentration where emissions are more intense than in surrounding areas. These observations shed light on the dynamic processes occurring at the heart of Andromeda and deepen our understanding of galactic nuclei. The supermassive black hole at the heart of the Andromeda Galaxy commands immense gravitational influence, with its mass estimated to range from 1.1 to 2.3 multiplied by 10 to the power of 8 solar masses, or approximately 110 to 230 million times the mass of our Sun. Supermassive black holes are believed to be common fixtures in the centers of galaxies, including our own Milky Way, and their presence profoundly shapes the evolution and dynamics of these cosmic structures. When matter, such as gas and stars, ventures too close to a supermassive black hole, it forms an accretion disk around it. This disk, comprised of swirling material, heats up and emits intense radiation across various wavelengths, contributing to the luminosity of the active galactic nucleus. Astronomers observe a brighter point of concentration near the central supermassive black hole in the Andromeda Galaxy, a consequence of the unique gravitational interactions between the black hole and the surrounding stars. Within the heart of the Andromeda Galaxy, the supermassive black hole exerts an immensely powerful gravitational pull on the surrounding stars, influencing their orbits. These stars trace elliptical paths akin to planets orbiting the Sun in our solar system. At the point of closest approach to the black hole, known as the perihelion, gravitational forces reach their zenith, causing stars to accelerate to higher speeds and become more densely clustered around the black hole. This concentration of stars and the associated release of radiation contribute to the brighter point of concentration observed in the galactic core of Andromeda. In addition to its supermassive black hole, Andromeda boasts an abundance of globular clusters, dense groupings of stars orbiting around the galactic center. These clusters, estimated to number around 46 in Andromeda, offer valuable insights into the galaxy's cosmic history and interactions with smaller galaxies over billions of years. The presence of these globular clusters suggests that Andromeda has been an active participant in galactic cannibalism, assimilating stars and other components from smaller galactic companions that fall within its gravitational influence. Furthermore, recent observations and analyses hint at a potential transformation underway in the Andromeda Galaxy, transitioning from a typical spiral galaxy to a relatively rare type known as a ring galaxy. Ring galaxies are characterized by circular or elliptical ring-like structures composed of bright, young, and blue stars surrounding a central region with relatively less luminous matter. This transition, if confirmed, would add to the galaxy's intrigue and highlight the dynamic nature of cosmic evolution. Ring galaxies can be classified into 2 primary types: O-type and type. O-type ring galaxies feature centrally located nuclei and smooth, regular rings, while type ring galaxies have off-center nuclei and more irregular ring shapes. These ring galaxies are considered rare cosmic phenomena, with only approximately 1 in 10,000 galaxies classified as such. Astronomers have proposed 2 main mechanisms for the formation of ring galaxies. Firstly, they can form through the collision of 2 or more galaxies. Alternatively, a smaller galaxy passing through the center of a larger galaxy can trigger the formation of a ring-like structure. Examples of ring galaxies thought to have formed through galactic collisions include the Cartwheel Galaxy, Galaxy Param 20264, and AR-147, showcasing the intricate interplay of cosmic dynamics. However, what's currently unfolding is even more intriguing. Scientists predict that the Milky Way galaxy and the Andromeda galaxy are on a collision course and will eventually merge to form a new supergalaxy. This colossal event has garnered attention worldwide, even inspiring playful nicknames like Milkomeda or Milkdromeda. While these nicknames may evoke whimsy, the consequences of this merger for humanity could be profound. As the two galaxies approach each other, their immense gravitational forces will distort each other's shapes, leading to tidal interactions where stars, gas, and dust are pulled between the galaxies. Eventually, the galaxies will overlap, causing mayhem and destruction. As the merging process progresses, stars, gas clouds, and dust clouds from both galaxies will interact and mix together, potentially forming new star clusters and structures within the newly merged galaxy. The collision will trigger bursts of star formation in regions where gas clouds collide and compress, creating new stellar nurseries. The merging process will also have significant effects on Earth. The alterations in the solar system's environment could impact Earth's climate and weather patterns, potentially leading to disruptions in habitats, shifts in biodiversity, and local extinctions. Changes in temperature, precipitation, and weather events may occur globally, influencing the distribution of vegetation and animal habitats. Furthermore, an increase in cosmic radiation within the intergalactic region could impact Earth's atmosphere, including the ozone layer, potentially affecting climate patterns and essential processes for plant and animal life. The merging of galaxies could thus have far-reaching consequences for life on Earth, highlighting the interconnectedness of cosmic events and terrestrial ecosystems. As climate and ecosystems undergo transformation, habitats for various species may become less hospitable or shift entirely. Many animal species rely on specific migration patterns for breeding, foraging, and survival. Disruptions in these migration routes and timings due to changing habitats and climate could pose challenges in finding food, water, and suitable breeding sites. The shifting climate and habitats may also lead to changes in biodiversity within ecosystems. While some species may thrive in the new conditions, others may struggle to adapt, potentially leading to local extinctions. Increased competition for resources could occur, and new opportunities might emerge for certain species to flourish in the altered ecosystems. Unfortunately, disruptions in habitats and migration patterns can have cascading effects on the entire ecosystem, potentially resulting in the loss of certain species from specific regions or habitats. While these changes are concerning, it's essential to note that the merger of the Milky Way and Andromeda galaxies won't happen overnight. The collision is projected to begin approximately 4 billion years from now, with the entire merging process taking another 2 billion years to complete. By that time, our Sun is expected to evolve into a red giant, rendering our solar system uninhabitable long before the galactic merger occurs. If descendants of our species or other life forms exist billions of years from now, they will likely be vastly different from us in evolutionary history. The fate of our solar system within the new supergalaxy remains uncertain, with possibilities ranging from ejection into the intergalactic medium to incorporation into the new galactic structure. The stability of the new galactic structure will influence the potential for habitable planets to exist within it. While liquid water is considered crucial for the development and sustenance of life, the interaction between stars and potential gravitational disturbances may impact planetary orbits and environmental conditions. Life that emerges in the new galaxy would likely undergo adaptation to its specific environment, potentially giving rise to unique forms of life distinct from those on Earth. However, it's unlikely that humans of today would be able to survive in this new galaxy without significant evolutionary changes. Ultimately, the evolution and sustainability of life in the new galaxy will depend on various factors, including the specific conditions of the environment and the ability of organisms to adapt to them. While the merger of galaxies presents intriguing possibilities for the emergence of new forms of life, it also underscores the dynamic nature of the cosmos and the continuous evolution of life within it. As scientists continue to study Andromeda, they have discovered that this galaxy not only holds a wealth of information about cosmic evolution, but also provides a unique opportunity to understand dark matter. Dark matter, which makes up a significant portion of the universe's mass, remains elusive and poorly understood. Observations of Andromeda's rotation and the behavior of its stars allow astronomers to infer the presence and distribution of dark matter within the galaxy, contributing to a broader understanding of its role in galaxy formation. Furthermore, Andromeda serves as a laboratory for examining galactic dynamics and star formation processes. Its diverse stellar populations, including older stars and young, massive stars, offer insights into various evolutionary stages of galaxies. The interactions with its satellite galaxies, such as M32 and M110, also provide evidence of how smaller galaxies influence larger ones over time.